Hello friends, welcome to Net Chemistry. We were seeing electrocyclic ring closure reactions, right? The last video we were discussing about electrocyclic ring closure reactions. Today we will see how the electrocyclic ring opening is happening. See, both electrocyclic ring opening and ring closure reactions are reversible reaction. So whatever the rotatory mode you have taken for ring closure reaction, the same rotatory mode only you have to take for the ring opening reaction. Okay, shall we see how it is coming? See, last day while ring closure we have seen cyclobutene is forming from 1,3-butadiene, right? 1,3-butadiene. The ring closure is happening and cyclobutene is forming. Under thermal condition, what was the rotatory mode is symmetrically allowed product. Cone rotation was giving us a symmetrically allowed product. While ring opening also you have to take the same rotatory mode. Okay, so cyclobutene under photochemical condition it is converting to 1,3-butadiene. Here which rotatory mode was allowed? This rotation was allowed for ring closure. The same thing will be happening for ring opening reaction also. Clear? Same way, if you are taking cyclohexadiene under thermal condition, this rotatory mode will give you the symmetrically allowed product. Okay. So, cyclohexadiene while ring opening under thermal condition, this rotation is the symmetrically allowed product. You are getting 1,3,5-hexatriene, right? The same way cyclohexadiene, if you see cyclohexadiene under photochemical condition, cone rotation will give you the symmetrically allowed product. Is it clear now? Because ring opening and ring closures are reversible process. What rotatory mode you have taken for ring closure, the same rotatory mode you have to take for ring opening reactions also. It is very clear now. You know what is cone rotation, what is this rotation under photochemical condition and under thermal condition. Foreign system, under thermal condition cone rotation, for foreign system photochemical condition this rotation will give you symmetrically allowed product. While ring opening also the same way you have to take. And here if you see for n+2 system under delta condition, under thermal condition, this rotatory mode was giving the symmetrically allowed product. While ring opening reaction also you have to take the same rotatory mode. Is it clear for you? We will see some of the example with the substitution. We will see some examples. I am writing a cyclobutene. Okay, ring opening reaction. This under thermal condition and under photochemical condition. Okay, two conditions we will see the same product, how the ring opening is happening. Okay, here under thermal condition what rotation will give you the symmetrically allowed product for a foreign system? Cone rotation will give you the symmetrically allowed product, right? So I am doing a cone rotation here. Cone rotation means both the bonds rotate in the same direction, right? So under thermal condition, cone rotation will give you the symmetrically allowed product. Either both the bonds rotate in clockwise or else both the bonds can rotate in anti-clockwise, right? So first we will see both the bonds rotate in clockwise direction. So I am getting a product of 1,3-butadiene, right? 1,3-butadiene, it is a cone rotation, so CH3 will come inside, right? And hydrogen will be out. Like this only you are getting while cone rotation. And here also the same way you will get CH3 will go out, right? CH3 will be outside and hydrogen will come inside. This we can say as product A. Okay, and one more possibility is there, both bonds rotate in anti-clockwise direction. Okay, both bonds now rotate in the anti-clockwise direction. I am seeing the product 1,3-butadiene. If it is rotating like this, CH3 will go away, right? And hydrogen will come inside, right? Then this CH3 will come inside and hydrogen will go out, right? Yes, CH3 will come inside, hydrogen will go out. Okay, so both bonds rotate in clockwise, both bonds rotate in anti-clockwise. Under thermal condition, cone rotation will give you the same product, right? Both clockwise if you see, both anti-clockwise you see, both the products same you are getting. Now come to the photochemical condition, cyclobutene. Under photochemical condition, which rotatory mode is symmetrically allowed product? You are getting symmetrically allowed product by disrotation, right? Disrotation will give you the symmetrically allowed product. So I am doing a disrotation here. One is in the clockwise direction and then the other will be in the anti-clockwise direction, correct? So ring opening has happening, 1,3-butadiene is forming. The ring as one is in the clockwise direction I am writing. So if it is rotating like this, CH3 will go inside, right, and hydrogen will be out. Clear? Here also CH3 will come inside, right, and hydrogen will be out. This is the product, right, you are getting. And one more possibility is there. This bond will be in the anti-clockwise direction and this will be in the clockwise direction. Both sides we are seeing, okay, we are getting the same product or not. Both side rotation we are seeing. Here we have seen both clockwise and both anti-clockwise, you got the same product. The same way you are seeing, one is in the clockwise, one is in the anti-clockwise we have seen. Here again I am seeing this bond in anti-clockwise and this bond in clockwise direction, okay. If this bond is in anti-clockwise, what will happen? CH3 will go out and hydrogen will come inside. So CH3 is out and hydrogen will be inside. And if it is in the clockwise direction, CH3 will go out, right? Clockwise direction, CH3 will be out and hydrogen will be inside, right? So two products are formed, A and B. You got two products. Whether these two products are same? No. If you see here, first rotation what I have taken clockwise and anti-clockwise, like this I have taken. So CH3, both CH3 has come near, right, towards inside it has come, and this CH3 group if you are seeing, that is away from. If you are seeing in the product A, two CH3 groups are sterically crowded, okay. Both products have formed by disrotation only, but if you see these two CH3 groups are sterically crowded more than A, so the product B is exclusively forming. While doing the disrotation, you have to see that and you have to write the product, okay. If both products are formed by disrotation only, but one disrotation if you are taking like this, it will be a sterically crowded product you are getting. So B product is forming exclusively. Now we will see another example. So this ring opening I am taking under photochemical condition, this product, okay. This is a trans isomer. Yesterday what we have got, while ring closure we have seen how the trans isomer and cis isomer you are getting. So the same products I am taking for ring open, same reactant I am taking for ring opening also. Here if I am taking H2 condition, photochemical condition, 4N system will prefer the disrotatory modes. Disrotatory mode will give the symmetrically allowed product. So I am doing a disrotation first. One is in the clockwise and the other will be in the anti-clockwise direction, okay. So ring opening is happening. So if you are rotating like this, CH3 group will go inside, right? CH3 will go inside and hydrogen will be out. The same way if you are rotating like this, hydrogen will come inside and CH3 will be away, right? That is the first option you have. Now I am taking the first bond is in anti-clockwise and this will be in the clockwise. Both disrotation only. I am just seeing the ulta, whether you are getting the two types of product we have to see. So if it is rotating the anti-clockwise, CH3 will go away and hydrogen will be, it is rotating like this, right? CH3 will be outside and hydrogen will be inside, right? Then this is rotating in the clockwise direction, then hydrogen will go out and CH3 will come inside, right? CH3 will be inside and hydrogen will be out. Both the products are same, right? Both the CH3 hydrogen inside, here also hydrogen and CH3 is inside. There is no difference. Both A and B products are equivalent product, right? This both products are same product you are getting. Now you come to the thermal condition. For an system, thermal condition, what is the rotatory mode symmetrically allowed product you are getting? Cone rotation will give you the symmetrically allowed product, right? So I am taking a cone rotation here. Ring opening has happened, 1,3-butadiene. So cone rotation, both bonds rotate in the same direction, right? So both, first I have taken the clockwise direction. Clockwise direction it is rotating means CH3 will come inside and hydrogen will be out, right? Then here also cone rotation I am taking. Hydrogen will be out and CH3 will be inside, right? And the second option I am taking both bonds anti-clockwise, okay? Now both bonds will rotate to anti-clockwise. So ring opening is happening. We will see this is anti-clockwise. So CH3 will come out, right? And hydrogen will be inside. Here also anti-clockwise rotation. Hydrogen will be inside and CH3 will be out. If you are seeing two CH3 groups are sterically crowded in the first rotation, right? And here it is not steric crowded. So the bigger group you have to take a rotatory mode in such a way that the bigger group always stay far away to each other. Okay, clear for you? And in this case also some electron withdrawing groups are there, like aldehyde groups and all is coming. Even if it is a bigger group also, you have to keep the rotation in such a way that the group is coming inward to the double bond. Why? There is a secondary orbital interaction that will give you a stable product. So that electron withdrawing group like aldehyde anol is present, you should prefer this product. But if it is CH3 like that electron releasing group, you have to keep it away each other. Because of the steric crowding, the product will not be stable. Clear? Okay, I have taken an example with a CHO group, aldehyde group, electron withdrawing group. What I have said, when an electron withdrawing group is present, it has projected inward to C double bond C. Okay, this double bond inward side it has to project. Why it has to do like that? Electron withdrawing group will give extraordinary stability to the product with the secondary orbital interaction. Okay, C double bond that group and C double bond C, that both will interact and the product will be a stable product. Okay, we will see how the product will be. Here what rotatory mode is symmetrically allowed product you are getting? Disrotation, right? So I am taking a disrotation here. Disrotation means both bonds in opposite direction, right? I am taking a clockwise here, then I have to take an anti-clockwise here, right? First product I am writing. So hydrogen, both side hydrogen only, right? Both side hydrogen. And now CHO group, right? This is the CHO group and hydrogen will be out, right? And the second product I am writing, one is in the anti-clockwise direction and other will be in the clockwise direction. One is in anti-clockwise, this will be in the clockwise direction. So I am writing the product. What product you are getting? This side both hydrogen only you are getting. And here CHO is going away, right? CHO and here hydrogen. If this is the case, if this is the larger group if you are getting, you have to choose this product. This product will form exclusively because of stability due to secondary orbital interaction. What? Secondary orbital interaction. All these things we will study, okay? How the stability of what is steric effect, what is secondary orbital interaction, electron releasing, electron withdrawing, all these things we will study. Now you keep in mind this is because of secondary orbital interaction. This CHO group, electron withdrawing group is coming inside, means this C double bond C will be stable. So you have to select this product. This product is forming exclusively. Now we will see the thermal condition. Thermal condition, what is symmetrically allowed rotation, cone rotatory mode, right? So I am taking a cone rotation, both bonds rotate in same direction, right? So ring opening is happening. So both bonds rotate in same direction. This side both hydrogen only. And if you see, CHO will go out, right? And hydrogen will be inside this rotation. Now I will see both bonds rotate in anti-clockwise. Okay, both bonds rotate in the anti-clockwise direction. Now this is the product B. So both side hydrogen here and CHO will come inside, right? CHO will come inside and hydrogen will be out. In this, which product will be exclusively forming? This product will be forming, right? Because the CHO group is inward secondary orbital interaction. This is the stable product. A and B is forming, and this B you have to select the bigger group. CHO is inward, projecting inward. Okay, is it clear for you? This is how electrocyclic ring opening and ring closure. Whatever the rotatory mode you have taken for ring closure, the same rotatory mode only you have to take for the ring opening also. Is it clear? Now thermal condition, photochemical condition, what is the rotatory mode symmetrically allowed is clear for you. Now we will see. Yesterday one more thing I have said. This is the Friendlier molecular orbital method, right? To analyze which rotatory mode is symmetrically allowed based on your molecular orbital you have taken. Now we will see correlation method. One more method I have said, correlation method and Mobius-Huckel method. This both methods also giving you the selection rule to predict the symmetrically allowed product. Whether the same way, in that method also you will get a disrotation and conrotation. We will just see the correlation method, how based on what correlation method will be. Okay, now you will not have like explain this correlation method and all, like descriptive type of questions will not be there. In first time CSIR syllabus, the second half will be the descriptive type. At that time correlation method and all you have to draw the orbital and show how it will be. So this is for your information I am taking. Okay, just to see the correlation method, the same selection rule only you will be getting. Next we will see correlation diagram for electrocyclic ring opening and ring closure reaction. How we have to take a correlation diagram for both electrocyclic ring opening and ring closure, both together only, the same way only we have to take. Now you have seen electrocyclic ring opening and ring closure, same rotatory mode only, the same way only correlation diagram also. So this correlation diagram is based on the symmetry aspects of the molecule. Okay, we have seen how the molecular orbital symmetry, yes or no? We have seen in the starting of pericyclic reaction two symmetry elements I have said, plane of symmetry and C2 axis of symmetry. Based on that C2 axis of symmetry and plane of symmetry, you have to predict whether it is conrotation or disrotation. So what is the symmetry aspect based on correlation diagram? What they are saying, mirror plane symmetry or else plane of symmetry. Plane of symmetry is respect to the disrotatory mode. Plane of symmetry is with respect to the disrotation, and C2 axis of symmetry. Okay, C2 axis of symmetry is with respect to the conrotation. Okay, plane of symmetry is with respect to the disrotation and C2 axis of symmetry is with respect to the conrotation. I am always remembering C to C. C is with respect to the C conrotation and molecular plane of symmetry is respect to the disrotation. C you can remember and keep. Okay. Okay, anyhow you know what is under photochemical condition and thermal condition, what is the symmetrically allowed rotation, you know. The same only we are going to prove with this correlation diagram also. Okay, we will see how a correlation diagram is coming. Okay, I will draw and keep the correlation diagram. So here I have written and kept all the molecular orbitals. Here it is a ring closure cyclobutene and it is 1,3-butadiene. Okay, that you understand, right? This is a ring closure reaction, vice versa ring opening also. Okay, the same reactant and product you are getting, ring opening and ring closure. Okay, so molecular orbital I have written, no need to explain to you. In the first video I have written all this molecular orbital, you know now. So Psi 1, Psi 2, Psi 3 and Psi 4 molecular orbital. Here also I have written the same Psi 1, Psi Psi2, Psi3 and Psi4. Okay, molecular orbital we are taking and we are seeing. Now we will see first mirror plane symmetry. How the mirror plane symmetry? We have seen if it is a mirror plane symmetry, if you are taking, that is with respect to the disrotatory mode, right? So under thermal condition and photochemical condition we will see how the mirror plane symmetry is going to behave. Okay, here you say me, here it is a mirror plane symmetry present or what? Positive. If I am taking a mirror plane, it is symmetric, right? Here it is mirror plane symmetry is there. Here Psi1 positive, here it is mirror plane symmetry is there, right? Yes. So with respect to the mirror plane, it is symmetric. Now if I am taking here also mirror plane symmetry is there, right? Positive. Here also if I am taking mirror plane symmetry is there, right? But if you take here in this side too mirror plane symmetry, or if there it is mirror plane symmetry or anti-symmetry, here it is not mirror plane symmetric, it is anti-symmetric to mirror plane, right? If I am keeping a mirror plane here positive and negative, right? The same way if you see here I am taking a mirror plane symmetry, right? It is symmetric to the mirror plane. Here if I am taking, it is anti-symmetric, right? Is it clear? The first video I have explained how you have to take the mirror symmetry, right? Now if you see in the case of Psi3, here it is a positive and here it is a negative, it is very clear, it is anti-symmetric to mirror plane. Here also positive and negative, right? Mirror plane anti-symmetric, right? By looking into this itself you can identify where it is mirror plane. If I am keeping a mirror here, if it is positive and negative, you are getting a mirror plane symmetry. In the middle if you are getting, that is what I am checking. So mirror plane symmetry is wherever symmetric I have put S and wherever anti-symmetric I have put M. Now we will match this orbital. This is the method, correlation method. So Psi1, in this Psi1 mirror plane symmetric. So this will match like this. And if it is Psi2 mirror symmetric, here it is anti-symmetric. So mirror plane symmetry will be like this. And here it is anti-symmetric. Okay, this is the way. Here it is anti-symmetric. Okay, so this is the ground state and this is the excited state. You know, Psi1, Psi2 is the ground state and Psi3, Psi4 is the excited state. If this reaction is thermally allowed, then only ground state will interact with the ground state. Okay, this is mirror plane symmetry and mirror plane symmetry, this will interact with this, and the same way this has to interact with the ground state only. If it is interacting with the excited state, this is thermally not allowed. Okay, is it clear now? Ground state is interacting with the up to the first excited state. If it is the ground state is interacting with the first excited state, then this is photochemically allowed reaction. Okay, now it is clear for you. We have seen this all, we have taken a mirror plane symmetry. Mirror plane symmetry is respect to the disrotation, you know. Now if you see here, this is ground state is interacting with the excited state, first excited state, then it is a photochemically allowed reaction. Thermally not allowed but photochemically allowed. Okay, photochemically allowed process. Now is it clear? Photochemically allowed and disrotation. So I have taken a mirror plane symmetry. Mirror plane symmetry is always with respect to disrotation. The same way only Friend-Air molecular orbital method also said. Okay, with the HOMO only they have predicted that it is allowed through the disrotation. Now we will see the cone rotation. Cone rotation is C2 axis of symmetry. Now we will see same molecular orbital we will take and cone rotatory mode we will see. If it is interacting with the only ground state, then it will be thermally allowed. If it is interacting with the first excited state, then it will be photochemically allowed. We will see how the C2 axis of symmetry. Okay, now we will see the C2 rotation, right? C2 axis of symmetry for the same molecular orbital we will see. See, if you are not understanding this molecular orbital, please watch the first video about pericyclic reaction, all the molecular orbital, how to draw the molecular orbital, everything I have explained in that video. So again and again no need to tell. Now I am going to take the C2 axis of symmetry. Here you say me, if I am taking a C2 axis of symmetry, both orbitals are same, right? Molecular orbital positive and negative, positive and negative. If it is rotating also positive and negative, positive and negative. So C2 is symmetric, right? Here if I am taking a rotation here, positive and negative, if it is rotating, positive will come down and negative will go up, right? So C2 is anti-symmetric, right? Same way psi3 I am taking, here it is rotating, negative will come down and positive will go up, C2 is symmetric, right? And if you see here itself, if you are taking a C2 is anti-symmetric, right? Then here if you are taking a C2 axis of symmetry, C2 if you are taking rotation, if you are taking C2 is anti-symmetric, right? This is rotating, right? And here if you are taking a C2, it is symmetric, it is rotating and coming. C2 symmetric, these two lobes will come up if it is rotating. Then C2 is, here what is C2? C2 is anti-symmetric, right? Correct or not? Here C2 is symmetric, right? So this is the way C2 symmetric and anti-symmetric you have to write. Then you have to see here it is C2 anti-symmetric will match here, and if it is, you see here C2 symmetric and C2 symmetric, this both will be matching. And here if you see C2 symmetric and C2 anti-symmetric. So you say me the ground state, this is the ground state psi1 and psi2, ground state will interact with the ground state and excited state will be interacting with the excited state. Now the reaction is thermally allowed or photochemically allowed. Our question is that only, how the reaction is thermally allowed, how the reaction will be photochemically allowed. So you say me it is thermally allowed or photochemically allowed. If it was photochemically allowed, then the ground state will interact with the first excited state, right? Here there is no first excited state, only ground state interact with the ground state, excited state interact with the excited state. So this reaction is thermally allowed, photochemically not allowed. Thermally allowed. And C2 axis of symmetry is with respect to which rotation? Cone rotation. So thermally allowed, delta condition, cone rotation is allowed rotatory mode. This is the way they are justifying cone rotatory mode is allowed under thermal condition. I will repeat, it is in correlation method. If the ground state is interacting with the excited state, that reaction is photochemically allowed. If the ground state is interacting with the ground state, then that reaction is thermally allowed. And one more thing, the correlation method is based on symmetry aspects of the molecule. If it is a mirror plane symmetry, that is disrotatory mode, and C2 axis of symmetry, it is a cone rotatory mode. This is the summary of the topic what I have taught you today. Thermally allowed means ground state will interact with the ground state based on correlation diagram, and if it has to be photochemically allowed, then ground state will be interacting with the first excited state, okay? And then plane of symmetry is with respect to the disrotation, and C2 axis of symmetry is with respect to the cone rotation. From this you have seen under thermal condition, delta condition, for a 4n system, cone rotatory mode will give you a symmetrically allowed product, and under photochemical condition, HNO condition, for a 4n system, disrotatory mode will give you the symmetrically allowed product, right? This is the same conclusion we have made from Frendire molecular orbital method also, okay? Hope you understand it well. To be continued with the cycloaddition reaction. Thank you for watching.